Okay, so it says in the program that I'm going to use Ford circles as my geometric representation. But we're going to change this around a little bit, and we're going to do a picture that looks more like bricks. So we're going to make a geometric representation of the abundancy index function, and then we're going to use this picture to find patterns. So the abundancy index is a function that takes natural numbers to the set of rational numbers greater than or equal to 1. So to calculate the abundancy index of a natural number, so always counting numbers, we take the sum of divisors of that number and then divide by the number itself. So this function is really important for determining when perfect numbers occur. So a perfect number is a number who has an abundancy index equal to 2. 6 is the first perfect number, since if you sum up the divisors of 6, and this includes 6, it equals 12, which is 2 times 6, twice our original number. So even perfect numbers are well understood, but even the existence of an odd perfect number is a mystery. So that's what we're going for. So we'll start by creating our picture now. Here we have rational numbers that fall in the range from 1 to 2. Right now, we've grabbed 2 lines. We have rational numbers with denominators of 4, and then on top, rational numbers with a denominator of 5. So inside the rectangle, we have the fraction, and we're going to center that above where the number would fall if we had a number line at the bottom of our screen. So whenever we have an abundancy index, we'll color these squares blue. And since we know the abundancy index of 2, that's actually an index, we'll color these blue. So now we'll go through some more. The abundancy index of 1 is 1, so we'll move on pretty quickly. To calculate the abundancy index of 2, we sum up the divisors of 2, so just 1 plus 2. So we have 3, and then divide by 2. So we'll color 6/4 blue. Next, we have a prime number. The sum of divisors of a prime number is just our prime number plus 1. And so the abundancy index will be of the form p plus 1 divided by p. So we have 5 plus 1 over 5, or 6/5. Now, the sum of divisors function is multiplicative. This means that since 10 can be written as the product of 2 relatively prime numbers, we can write the sum of divisors of 10 as the product of the sum of divisors of 2 times the sum of divisors of 5. Now, you can only do this when you have 2 relatively prime numbers. You can't do like sum of divisors of 2 times sum of divisors of 2, only if they're relatively prime. So now we'll finish off our picture with the last 2. Now, for these 2 green squares here, we haven't found a number that has this abundancy index yet. We have 7/5 and 5/4. So we're going to leave these green. Now, if we continued this process, looking at denominators all the way up until 20, we get this picture. So here are 2 lines that we've already created. It's a pretty cool picture. So we have a lot of unknown bricks still. And so is it possible that we just haven't searched big enough numbers, and these are actually abundancy indices? Yeah, we haven't checked every number, so, but it turns out there are some numbers that can't possibly be abundancy indices of any number. And so we call these fractions abundancy outlaws. So we're going to look at those some more because it's kind of important. So the first class of abundancy outlaws was discovered by Paul Weiner. He noticed that if our fraction is in lowest terms and the sum of divisors of the denominator, if that is bigger than the numerator, then we have an abundancy outlaw. For instance, our 5/4 that we had before, this is already in lowest terms, and the sum of divisors of the denominator, so the sum of divisors of 4, is equal to 7. 1 plus 2 plus 4. And that's bigger than 5, our numerator. So we have an abundancy outlaw. In general, if n is a composite number, then n plus 1 over n is an abundancy outlaw. You can check it's in lowest terms, and the sum of divisors of a composite number is bigger than n plus 1. So here's what we get when we color all these abundancy outlaws of this form. And so in the first row over here, after 1, we have all the fractions of the form our number plus 1 divided by the number. So if we have a prime row, these are all abundancy indices, because they're all the form p plus 1 over p. That's the abundancy index of our prime number. But if we have a composite denominator, these are of the form n plus 1 over n, and those are abundancy outlaws. So we have the first row all figured out, but we don't always get so lucky. In fact, if we have a prime denominator, like 13, we can't even classify any of these fractions as abundancy outlaws yet. So if we continue this picture even more, this time zooming out and looking at fractions all the way up to 100, we get this. Looks pretty cool. So these pretty neat blue diagonal stripes, these are all fractions with the same numerator. So starting at the bottom here, we have 6, and then 24, and then 48, 96, and 116. This is a kind of cool pattern, but we're not exactly sure why that is. Most of these ones are not in lowest terms. So, and then also, there are some orange bricks scattered throughout here. These are Stanton-Holdner outlaws, which is another form of abundancy index outlaws. So if we took our picture that we had before, and we just sliced out all of the prime rows, so all the green rows that you see right here that have prime denominators, and we stacked them all up on top of each other, we'd get this picture. So as before, first column over right over here, these are all fractions of the form p plus 1 over p. Now this one down the middle, for any prime number that's bigger than 2, 2 in our prime number will be relatively prime. So if we calculate the abundancy index of 2 times our prime number, that gives us 3 times p plus 1 all over 2p. Now p plus 1, since a prime number plus 1, it'll be even. So when we put our fraction in lowest terms, we're left with a prime denominator. That's why we end up with this stripe here. Turns out we can do something similar to capture this stripe. That's purple. And so this time we need to require that our prime number is congruent to 1 mod 3. That means that 3 divides p plus 1. In this case, 3 and our prime number are going to be relatively prime. So we can split up our sum of divisors and calculate the abundancy index. So we get 4 times p plus 1 over 3p. When we put it in lowest terms, our 3 flies up to the top, and we're left with a prime denominator again. So that's how we get that next stripe. Now, if we look at our picture, we notice that we don't have any abundancy indices of the form p plus 2 over p. So we want to keep looking at those. They're probably outlaws. Now, we also have fractions of the form p plus 3 over p. Turns out these happen exactly when p and 1/2 p plus 1 are both prime. We can calculate the abundancy index of the product of these two prime numbers. And something really cool happens. The p plus 1s cancel out, and we're left with a prime denominator. So that's pretty neat. We can also generalize this a bit more, and we can find fractions of the form p plus k over p. And these all fall to the left of this purple line here. So the abundancy index function isn't just defined from 1 to 2, although a lot of the important things related to perfect numbers do happen within that range. So here's what we get if we zoomed out from 1 to 4. And then that's everything. Do you have any questions?
Paper's now open for questions.
Hi.
Hi. Can you go back to that prime denominator slide with the p plus 1?
Yeah.
Sorry, the p mod 1. Yeah, that. So that column on the left there is the 1 mod 3 column, right?
This
Right?
one that's purple right now?
Right.
Yep.
So can I do something similar with 2 mod 3? And is that the thing on the right of the big middle?
2 mod 3? No. Because why we're asking for 1 mod 3, and this is so that 3 divides p plus 1.
Okay.
To capture this row right here, that's actually 4 times a prime number. Is that the one that you're
That's
looking
what
at?
I'm looking at, yeah.
Yeah. And this gets really close to 7/4.
Mm-hmm.
Since the abundancy index of 4 is equal to 7/4.
Cool.
So yeah, that was another cool thing that, yep. Great.
I have a question,
Yeah.
actually. So the widths of those blocks, I'll call them, is that somehow, I mean, I missed it earlier, but is that somehow proportional to the fraction, or how are those displayed exactly?
Yeah, I stretched it so that the width of our rectangle, if we had a number line going along the bottom, our fraction that it describes lies directly in the middle. And then we stretch it out so that it fits, all of the lines fit. So, yeah.
Okay, if there are no other questions, let's thank our speaker again.